Hello, my name is Carter, and today we're going to be going over infinite series in preparation for the upcoming test. Now, there's a lot of content, and so I pre-compiled a list of review materials since it's such a big chapter. And I'm going to quickly go through that. I'll try to quickly go through that. It's probably going to take a bit. And this is going to be at least 2 videos, possibly 3 if this one goes long. I would just make it 1 video, but I guess it's nice to segment it. And then my channel has like 2 subscribers, so I can't really record long and post long videos. So the format's going to be go over this, which I'm just going to walk through, tell you the important things, and then we're going to do some problems on essentially everything but Taylor polynomials and power series or Taylor series and power series. And then we're going to have the second video on this AP style question for the Taylor series and some small power series problems. So let us get into this. The first thing you have to know is that a sequence is a list of numbers. In this case, we have an alternating sequence of ones, -1, 1, -1, 1, so on. And we're going to continue on that later. Well, everything builds upon that. So then we have important theorems, and these are going to be used when we're doing our tests and stuff. We have the limit as ln n over n is equal to 0, and that's using L'Hopital's rule. We got the nth root of n, the limit of that is equal to 1, and at the same time the nth root of x is also equal to 1. They're both equal to 1. We have the limit expansion of e to the x, which is 1 plus x over n to the nth power, quantity to the nth power. And then the limit as n approaches infinity, x to the n over n factorial, that's 0. The idea behind this is n factorial is like a larger value. It grows larger than x to the n does. It's a larger infinity in a kind of simple, not that accurate concept, but the answer is 0. So with an infinite series, we have it's the sum of an infinite sequence of numbers. Obviously, we just talked about sequences. An example, general example is that sine sigma, the summation from n equals 1 to infinity of a to the n. Now, let's go over some types of series. So we have an arithmetic series, and the sum's right there. And these are always divergent. An example is 2 plus 5 plus 8 plus 11. For each number, we're adding 3. And as you see, a equals 2, that's our starting value, and d equals 3, that is our, our increment. We have a geometric series, so the sum is right there. And it diverges if r is greater than or equal to 1, and converges if r is less than 1. An example of that would be 2 plus 4 plus 8 plus 16, and then we're starting with 2, and we're multiplying by 2, so a equals 2 and r equals 2. Now we have a harmonic series, which is just the summation of 1 over n, and that's always going to be divergent. That's a very important thing. You want to know the harmonic series. And we also have alternating series, which the idea behind that is it's a positive, negative, or negative, positive. And the error for an alternating series, this is very important, is the absolute value of the next term. So let's say we want to estimate some alternating series, and we use 5 terms to do so. The error would be less than the 6th term, the absolute value of it. So that's an important thing to note, and we'll go a little more into errors down below. For tests, we have a bunch, so you gotta say, but I'm gonna try to just go over them on an overview level, and you can read the details. I'll try to link this whole PDF in the video. So we have the n-term test. That's one of the most basic ones. Use that a lot for alternating series. Yeah, and it's not perfect because if you do the limit and you find that it equals 0, you're not actually it's not conclusive. It may or may not converge, but it definitely doesn't diverge. Then we have the integral test, and essentially you take the integral of this function, or you make the series a function, And then if the integral diverges, it diverges. If the integral converges, it converges. That's not hard. P-series, this is one of the easier ones, and so you just want to make sure you know it down pat. We have in the form 1 over n to the p. If p is greater than 1, it converges. If p is less than or equal to 1, it diverges. And then we have a logarithmic p-series, which is, obviously a variant p-series. And it's the same conditions for convergence and divergence. Now we also have the comparison test. This one was I feel like it's a little difficult to articulate in a comprehensible way, so I tried to do it 2 different ways. Essentially, what happens is, let's say you have a series, and you obviously want to see if it converges or diverges. Well, you can look at whether you can take a series that let's say a harmonic series, that always going to diverge, and if the original series is greater than that, and we know that our series diverges, then it's also going to diverge, that original series. And if it's less than that series, and the known series converges, then the other series converges. So I'd make sure you kind of understand that. I know my explanation really wasn't that great, so try to read that and understand that, because it is a very important tool. Now we have the limit comparison test. You can see there's a bunch of different conditions. It's similar in nature though. And why would we use it? Well, let's say we take the summation of 1 over n squared minus 2. Well, that is actually greater than 1 over n squared. And we know that 1 over n squared converges because of the p-series. It's 2 is greater than 1 in this case. And since, as I said, 1 over n squared minus 2 is actually greater than 1 over n squared, the irregular comparison test is inconclusive. So this isn't a case where we would use the limit comparison test. Now, for the ratio test, this is a very important one, especially when you get the power series. Essentially, every time you see a factorial, you're going to say, okay, probably going to be using the ratio test. And so what you do for this, you can read it. The series converges if rho is less than 1, diverges if rho is greater than 1, and inconclusive if it equals 1. Essentially, take the n plus 1 term over the nth term, and you take the absolute value of that. Pretty simple. Now we have the nth root test. This one, I feel like you don't see it as much, but it's still important to know, obviously. This is actually an accident. I kind of copied, but you don't see factorials. You might use it if you see like a giant expression raised to the nth power, then obviously you can just undo that with the nth root, but same criteria. So then we have types of convergence. We have absolute and conditional. So it's absolute when the alternating series converges as well as the absolute series converges, and it's conditional when the alternating series converges but the absolute series diverges. We have an example there. So now we have power series, and for the power series, it's in that form as we see. And then an important thing to note, for the power series, this comes up a lot, but it can be applied to other things, is the interval of convergence. And essentially the interval of convergence states the values of x that make a series converge. So again, you can apply this to like a geometric series per se, and find the values of x such that the geometric series converges. Hypothetically, you can even find the values of x such that the series diverges. I don't know. Oh, my bad. Oh, man. Sorry. Okay. But that's that. So then we have the Taylor and Maclaurin series. I don't know. And essentially, these are very big. You're probably going to get an FRQ about one of these. It's kind of guaranteed on your AP test, I feel like. And we can see the expansion for the general expansion for Taylor series and the general expansion for Maclaurin series. Make sure you understand that. It follows a very distinct pattern, as all these things do, so it's not the hardest thing to understand, but there's a lot going on here, but just make sure you understand that, because that's a very important expansion. Now we also have the Lagrange error bound, And previously we kind of briefly talked about the error for an alternating series. So essentially, if a series is not alternating, how would you find the error bound? Error bound. That would be the Lagrange's error bound. Um, and we give it here. Essentially, it's like the n+1 term of a Taylor series, and that's kind of that. Now, for common power series, these are very important to know. You're probably going to get a question about this. Essentially, the reason why you want to know this, you can always derive this, and it's not very difficult to do so, but I don't think you really want to, so it's better just to know it. Let's say you need to find the power series for x e to the x. Instead of deriving, differentiating x e to the x over and over again, you can just multiply the power series for e to the x by x, and then you have it easy. So here they are. Just kind of make sure you know them. They're important. E to the x probably the most important. That always shows up. But regardless, let us do some problems. So I precompiled a list and I'm going to go through them to kind of cover a little bit of everything. So I'm just going to give a heading. And essentially this kind of hones in on convergence or divergence of a series. So we're going to do this first one. And I kind of thought this was interesting. It's not very difficult, but it's the quantity of e over pi to the nth power. And this one's actually extremely easy to solve because we know that e is less than pi. Therefore, this r value, we can call it, is less than 1. Therefore, the series converges by the definition of a geometric series. Converges by a geometric series. So that one was easy. Now the second one. So we're going to have the summation from n equals 0 actually to infinity of 3/4 to the nth power. So I'm sorry, I keep saying I'm a little tired. What we're going to do here is you're going to see this is in the exact same form as the problem we just did. So you might be like, okay, well, just use the definition of a geometric series. And you're completely right in that, but I just want to quickly show you something. Is when we do the limit test, and remember the limit test takes the nth term, so we're going to say 3/4 to the nth power. And now as this thing approaches, as n approaches infinity, this whole limit's going to approach 0 because we're essentially compounding this 3/4 and it's going to become smaller and smaller and smaller and smaller and approach 0. So this is actually an inconclusive test. Now luckily we have another method that we talked about, that's our geometric series, so it actually converges by the definition of a geometric series, by the geometric series. And that is obviously because r is less than 1, that's the value of r. So right now I just want to highlight it so it's a little clearer. We have converges and converges. And this I just wanted to show that you're going to have different methods of solving something, and sometimes they're just not going to work. You're not going to get the right answer. Or, I mean, you're not going to get a answer. You're never going to get the wrong answer unless you do it wrong. But you're just not going to get a answer. As we see, this was inconclusive. So sometimes that just happens, and you got to think again and find a different one. So we're going to move on, though. So the summation from n equals 1 to infinity of 1 over n squared. Now, this is a very simple p-series problem, but we're also going to evaluate this using the integral test, just to get a little bit of practice. Just a quick aside is I don't really think the integral test is too prevalent, but we're still going to try it here. So we're going to say the integral of 1 over x squared dx and we want to do that from 1 to infinity. So that's an improper integral, so I'm going to rewrite that. Integral of 1 to b, 1 over x squared dx. Now we're going to solve the integral, and it's going to be negative x, and then we got this line 1 to b, I guess. So that would be negative b to plus 1, negative b plus 1. I feel like oh yeah, duh. I knew this one was off there. That's my bad. It's negative 1 over x squared. That fixes it. So now we have negative 1 over b and plus 1. So this approaches 0 because, I guess it is 0 because b is equal to infinity. And I'm messing up. Wow, I'm sorry. The limit is also carried over. But this is 0, so we have a 1 as the value as the integral, and because the integral converges, therefore our series converges. And again, as I said, that is a very simple p-series problem. It's just p is 2 is greater than 1, but we wanted to try something a little different, and that goes to show that there's multiple ways to solve a problem. Now, this one we're actually going to solve with p-series. Clearly, you're going to see that p is less than 1. It's 1/2 in this case, so it diverges by p-series. Okay, and I forgot, but oh, that's the wrong one. There we go. Highlight a little bit. Now we have the summation from n equals 1 to infinity of 1 over n squared, and that's minus 5. So now clearly you can see we can't use a simple nth term test or something like that. We're going to have to think a little bit outside the box. And simply put, the easiest way to do this is probably a limit comparison test. Oh my god, I skipped the problem. So at first we're going to do plus, and this is something did look wrong. We're going to do plus, and now we're going to use just a straight comparison test, because what we're going to see is we know what 1 over n squared is. That series converges by the p-series. And if we look, we can see that 1 over n squared plus 5 is less than 1 over n squared. And now that fulfills our requirements for this comparison test. So the series converges as well. And essentially what we did is we said, okay, we can't really evaluate that straight up. Is there something that we know the value of and that's very similar? Yeah, it's 1 over n squared. Then we have to ask ourselves, is 1 over n squared greater than this value? And the answer was yes, so both of the series converge. So now we have number 6, and this is what I was accidentally almost did, is n squared minus 5. And what you're going to see, just kind of intuitively, 1 over n squared is less than this, so we can't use our comparison test. So what we have to do is our limit comparison test. And we're going to say that the limit as n approaches infinity with absolute value 1 over n squared minus 5 over 1 over n squared is equal to the limit as n approaches infinity of n squared over n squared minus 5. And clearly this limit is going to equal 0. Sorry, it's going to equal 1. And because this limit equals 1, we can say that it converges. Okay. On to 7. And n equals 1 to infinity, 1 over n plus 2. And what we're going to do for this one is another limit comparison test. So we're going to say the limit, obviously we're going to compare this one to the harmonic series, just 1 over n. So we're going to say 1 over n plus 2 over 1 over n. And that's going to be equal to the limit as n approaches infinity of n over n plus 2. And again, that's going to equal 1. So again, we are going to get, oh, no, what did I do? 1 second. Um, 1 over n plus 2 is equal to, yeah, okay. So this diverges. I think I messed up the rule. Yeah, I don't know, I think I just messed that up. Okay, so we'll say this diverges instead. I'm trying to think exactly where my thinking is. I don't really want to stop the video too much though. Oh my God. Okay, I'm sorry. I got the rules confused real quick. This one's actually really simple, and I was correct in saying this, but I forgot a part, so that is my bad. But I guess it's a good lesson in a sense. So essentially, what I did wrong is I forgot what the limit comparison test actually says. So let's make sure we understand this. If it equals 1, that means the limits, both of them, either converge or diverge. They both do the same thing. So what I forgot is that, I forgot that. So in this case, it does converge because, um, uh, I didn't write it anywhere, I guess. 1 over n squares converges. So they both converge. Now, in this case, 1 over n diverges, so 1 over n plus 2 also diverges. And I'm sorry for that error, but at least we rectified it. So we're gonna do, I think, one more problem. I don't want to make the video too long in case it doesn't upload. But we'll do this one, I guess, and then we'll call it. So this refers to our absolute convergence, idea of absolute convergence. So we're gonna have an alternating series, and it's over n squared. I know n squared is getting a lot of love today. And what we can say is that since the summation from n equals 1 to infinity of 1 over n squared converges, this series converges absolutely. The series converges absolutely. And that is that. That one's really simple. And so I have, I think, 4 more problems, and then a few more for like what I scheduled for the other video, but I'm gonna end this one now. If you wanna hear a little bit more about here, I'll give a spoiler real quick. I'll just pull it up. 1 second. So in the end of the next video, we're gonna do ratio test, comparison test with a ratio test thing, and a nth root test and the limit test. And that's kind of that. And then we're also going to talk about error bounds and intervals of convergence. And then we're going to do a Maclaurin series problem. So that's going to be that. And yeah, so I'll see you in the next video. Thanks.